Hello everyone, my name is Mukta Devnath. I'm a research fellow at Indian Statistical Institute, Kolkata. Here I'm going to present my work, Aggregate Encryption, Individual Decryption for FPGA Bitstream Protection on Cloud. This work is done in collaboration with Indian Statistical Institute, Kolkata, University College Cork, Ireland, and University of Calcutta, Kolkata. Here is a brief outline of our work. Let's begin with the popularity of FPGAs in cloud environment. Now, why FPGAs are so popular in the cloud environment? It is because of its reconfigurable nature, which allows it to dynamically adapt to different hardware at different point of time, as we can see in the figure. Second is the FPGAs are gaining popularity as major accelerators in the cloud environment because of its improved throughput, reduced latency, and low power consumption. FPGAs are integrated by major cloud providers like the Google Cloud Platform, Amazon AWS, Oracle Cloud, and Microsoft Azure. FPGA allows the deployment of third-party IP core in it. The cloud service provider processes the user data and offers the same to the FPGA. Now let us see an FPGA-based cloud system model. As we can see, it has the typical cloud CPUs, cloud GPUs, and cloud storages, along with the FPGA resource pool and the IP resource pool. And this system model, the key participants in this model are the cloud service provider, the FPGA vendors, the IP providers, and the users. The cloud service providers deploys FPGA from various FPGA vendors to the cloud FPGA pool, and also the CSP buys third-party IPs from the IP providers and store it in the IP resource pool. The user submit their task to the cloud and get back the process result. Now in this system model, there could be various associated threats. One is the external unauthorized access. So an external agent may try to intercept the bitstream while the bitstream is in transit within the cloud environment. Another is the information leakage among IP providers. Now, one IP provider may try to intercept the bitstream of another IP provider while they're executing on the same FPGA. Now, there are various security issues related to the FPGA IP bitstream cloud environment. Some of the well-known attacks that could be imposed are the man-in-the-middle attack, where an attacker may try to steal the bitstream. Another is the original bitstream could be replaced by a counterfeit bitstream by malicious code insertion like hardware Trojan horses. There could be side channel attacks too. So the privileged informations about the IP could be obtained from the side channel informations of FPGA. So to mitigate such security issues, researchers have proposed different techniques over the time to protect the IP in the cloud environment. However, we find four major limitations in the existing works that motivates us for our framework. One is the individual encryption scheme. The existing works often encrypts a bitstream for a particular FPGA. So this leads to the bitstream being tied to a specific FPGA. So this limits the capacity of a CSP to measure its own resources. Another is the third-party involvement. The existing works rely on an external third party for the cryptographic key provisioning. So this may lead to unintentional security risk. Another is the FPGA resource overhead. Now, most of the existing works, either they require extra hardware attached to the FPGA or an extra processor on the FPGA for their cryptographic key storage or protection. Now, our objective is to address the four limitations of the previous works and provide an end-to-end security to the FPGA bitstream while moving to the cloud environment. So how do we do this? We follow an aggregate encryption scheme instead of individual encryption, where a bitstream is encrypted for a group of FPGAs rather than a particular FPGA. So this leads to the decoupling of the bitstream from a specific FPGA. This, in turn, it increases the efficiency of the cloud service provider to manage their own resources. We do not involve any external third party except we trust only the FPGA vendors. Also, we require low FPGA resource overhead since most of our cryptographic operations are performed in software, thus very less hardware requirements. So to fulfill our objective, we depend on a technique called the key aggregation. This process allows for the efficient management of cryptographic keys in scenario where multiple keys are involved, such as the multi-user system, the cloud computing environment, secure data sharing. So here we present our work, aggregate encryption and individual decryption, and we name it as AgEID. Now, AgEID's key aggregation steps are derived from existing work on key aggregation, which is called as the pre-aggregate crypto system or KS. Now, a famous work by Bug et al. They have already applied the KSC framework to secure Bitstream in the cloud environment in a multi-tenant environment. Now, we get our inspiration from these two works, and we propose a new aggregate key generation algorithm with corresponding encrypt and decrypt operation. Now here we show the difference between the KSC key aggregation scheme and the AgEID key aggregation scheme. As we can see in the figure, in the KSC key aggregation scheme, the messages are encrypted individually based on their associated unique identities. Now, this process is managed by a system administrator who generates the master public key, the master secret key, and also the system administrator generates an aggregate key for any arbitrary subset of these messages so that the key could be used to decrypt the ciphertext belonging to that subset. Suppose here the example is shown as an aggregate key SK1 and 3 is generated that is used to decrypt the ciphertext C1 and C3, whereas the SK13 cannot decrypt the ciphertext C2. Thus, this is their aggregate, this is their individual encryption scheme. However, they allow aggregate decryption. Now, AgEID's requirement is completely opposite of KSC requirement. So, what AgEID does is we follow an aggregate encryption scheme. So, we can see that here we encrypt a message M1 for a set of entities identified by their unique entity IDs, and the process is managed by entity administrator who generates the aggregate key, the master secret key, and the individual private keys for the entities. So here, for example, we show that for two entity sets S1 and S2, S1 with identities 1 and 3, S2 with identities 2 and 4, the message M1 is decrypted with KS1 and 3 and KS1 and KS2 and 4. So after the aggregate encryption is performed, the ciphertext produced for the entity set S1 is C1 and ciphertext produced for the entity set S2 is C2. Now C1 could be decrypted on for the entities 1 and entity 3, but will fail to get decrypted for entity 2 and entity 4. However, C3 could be decrypted for entity 2 and entity 4, but cannot be decrypted for entity 1 and entity 3. So now the decryption operation takes place using the entities individual private keys denoted by D1, D2, D3, and D4. So this is the difference between the key aggregation in KC and key aggregation in AgEID. Now, we prove the correctness of the key aggregation in AgEID in our paper in details. Here we state the theorem which states that for a message M, the decryption of the ciphertext C produced by the AgEID's encryption scheme will precisely yield the original message. Now, to prove this theorem, we take the help of two lemmata from the properties of bilinear pairing on elliptic curves, which we state here, and we give the details of this in our paper. Here we show an example how AgEID finds its application in the cloud environment. And we show it with one FPGA vendor and one IP provider. Now, the cloud service provider, um, in step 1, the cloud service provider forms cluster of the FPGA boards. Now, we show an example how the cluster is formed. Suppose here cluster 1 is formed with FPGA 1 and FPGA 3 belonging to the same FPGA family of boards, which is the Zing 7000. Another, as an example, we show a cluster 2 formed with FPGA 2 and 4 from the family Zing Ultra Scale of FPGA boards. So after the cluster formation, the CSP requests the FPGA vendor for FPGAs in cluster. The purpose of the FPGA vendor in step 2 is to generate the AgEID parameters required for encryption and decryption. So the FPGA vendor performs these steps: the setup step, the key generation step, the extract steps to generate the public key, the aggregate key for encryption corresponding to each cluster, and the private key for each FPGA. This is the responsibility of the FPGA vendor to dump the individual private key and the AgEID decryption core on the FPGAs, and then they deploy the FPGAs in the cloud. And also the FPGA vendor sends the parameters, the public key parameters and the aggregate encryption key parameters to the cloud service provider. Now the cloud service provider requests for IPs from the IP provider for cluster of ports. So in the step 3, the encryption process takes place where the IP provider encrypts the bitstream using AES encryption, and the IP provider also encrypts the AES key using the AgEID encryption scheme, which is the aggregate encryption scheme. So after the encryption operation, the IP provider sends their encrypted bitstream along with the encrypted AES key to the cloud service provider. And for this encryption process, the IP providers request the public key and the aggregate key it receives from the cloud service provider. So after the encryption operation in step 4, we show the decryption operations of the agent, and the whole decryption process takes place on board. And when an encrypted bitstream along with this encrypted key is received on the FPGA board, the agent decrypt operation is first performed to obtain the AES key, and then with the help of this AES key, the bitstream decryption occurs using the AES decryption core to get back the original bitstream. So this is how AgEID is applied in the cloud environment. Next, we discuss about some of the experiments and results. So for our experimentation purpose, we actually developed 3 baselines. One, we designed a scenario 1, that is with cluster with boards from the same FPGA vendor and family, and a scenario 2 where cluster with boards from the same FPGA vendor but with the different families are formed. Another, we design a null one-to-one mechanism and we name it as AgEID, the individual encryption and individual decryption. So here is the result for bitstream encryption of AgEID versus AgEID. So the time requirement for bitstream encryption in scenario 1 and scenario 2 is shown here. So you can see that AgEID performance is superior than that of the AgEID. AgEID requires a constant time in scenario 1, whereas AgEID takes time increases linearly with increase in number of ports. In scenario 1, and in scenario 2, the number of bitstream encryption operations performed by AgEID is equal to the number of families of boards. So the time of AgEID slightly increases. However, it's still better than the AgEID approach. With similar explanation, we show the result for NHE efficiency, and we can see the same kind of result here also. The performance of AgEID is better than the AgEID. Next, we show the results of time for scenario 1 when we increase the size of the bitstream. With the increase in size of bitstream, the time required for encryption also increases. However, we see that AgEID performance is better since AgEID framework requires one-time bitstream encryption, irrespective of the AgEID approach, where the number of bitstream encryption operation increases with the number of ports. With similar explanation here, we show the energy efficiency result for AgEID and AgEID with various sizes of bitstream. Here also we see that AgEID performance is superior than AgEID. Now we discuss the result for key encryption. Now, AgEID's time requirement for key encryption is constant irrespective of scenario 1 and 2. Similarly, for energy also, the energy consumption of AgEID is constant. It is because AgEID, the key encryption operation is performed only once, um, as compared to AgEID, which requires the number of key encryption operation equal to the number of bots in the system. So next we discuss the key decryption performance of AgEID. For key decryption, AgEID uses a software decryption module which is executed on the ARM processor in the PS section of the modern FPGAs, and there is no hardware requirement. Now, for those FPGAs where an ARM processor is not available, we develop a hardware decryption module for AgEID which would be executed in the PS section of the FPGA with a reasonable resource overhead of 2 to 17%. Here is the overall performance of AgEID for hardware decryption. So we can see the performance of AgEID is quite reasonable. Next, we conclude this presentation with the following points, like AgEID crypto system successfully protects FPGA bitstream through secure key provisioning. The key aggregation technique of AgEID aids to significantly reduce the resource overhead, storage time, and energy for both key and bitstream encryption. AgEID enables the execution of bitstream on a group of FPGA ports while being encrypted as a whole, but decrypted separately on each port, significantly enhancing the flexibility of resource management for CSP. We aim to explore the authentication of bitstream using AgEID. We intend to implement cutting-edge cryptographic algorithm to address threats arising from advanced onboard FPGA attacks and large-scale quantum computing attacks. Now, for this work to be successfully completed, we acknowledge the Department of Science and Technology, SERP, Government of India for their grant. Now, these are some of the references that we use in our presentation. Thank you for your cooperation, and we regret that none of the authors could attend the conference. However, for any questions, you can mail to me at this mail ID. Thank you.